Hello, and welcome to the first in a series of videos we're going to be producing around the topics related to the use of formic acid in animal production. This first topic today is going to be on the principles of feed acidification. I will be your host, Joshua Genza. I'm the Global Technical Product Manager for Organic Acids in Novasil, and I'm working with Balchem to put together these videos to help you understand the value behind the use of our AMASIL line as a feed acidifier. First topic we need to get into is the basic effects of feed acidification. So first and foremost is the reduction of the pH of feed, which is what acidification means. This is important because this has additional benefits, such as the inhibition of biological feed contaminants and reduced acid binding capacity of the feed itself, which we'll get into a little bit later. When that feed that's been acidified is then consumed by the animal, you get the benefits of that continue on into the gut, such as the reduced pH in the early digestive tract, which is really important for nursery pigs, and the ability of the anion, so in this case the formate part of the formic acid, can bind with certain metal cations and have other effects that can promote digestibility, gut development, and gut health. So it's important to keep in mind that feed acidification is about more than just the pH of your feed. So getting into a little bit more into it, AMASIL exists in two states in solution, and this is an important concept that we'll spend a little bit of time on. AMASIL is an organic acid as opposed to an inorganic acid. And the differentiation here is that the organic acids do not fully dissociate in water. And so what it means is you set up an equilibrium between the dissociated state, which we have represented here in green, in which there's the negatively charged anion, the positively charged ion, and the undissociated state, which is represented in orange, in which they're still connected to each other and they're still, as a result, uncharged. This is significant because the dissociated acid is where you get the main effects. But there are limitations to this. Once they've dissociated, the positively charged and negatively charged ions cannot pass through the cell membrane, and so all of the effects are limited to whatever side of the cell membrane they happen to be on at the time. The most of this is going to take place extracellularly, but the undissociated acid is uncharged and as a result can freely pass through the cell membrane and then become dissociated in the more alkaline environment inside the cell. And as a result, this is where the benefit of organic acids come in, this ability to act on both sides of the cell membrane. So here's a small cartoon that really illustrates this. So you've got the green dissociated acids outside the cell membrane acting to affect cell membrane permeability, the hydrogen ion-based transport systems and those kinds of things, damaging extracellular structures. But you've also got the undissociated acid, which can be absorbed by the bacteria, dissociate in the higher pH environment inside the cell, and then affect changes there where it can interfere with DNA replication, energy metabolism, protein folding, and those kinds of things to increase the stress level on those bacteria. And this is illustrated very well in a study that was done by Chavarich et al. In 2002. And what they did is they took 4 different strains of Campylobacter and they inoculated feed. And then they acidified that feed with hydrochloric acid and formic acid and looked at how long it took each of these two acids at the same pH to eliminate detectable Campylobacter from the feed. And as you can see, represented in green at the pH of 4 and by the blue lines at the pH of 4.5, is that at both of these pHs, formic acid acted about 4 times faster than hydrochloric acid because of this combination of intracellular and extracellular effects. So if you're in the market for an acidifier, the first question you need to ask is, how do I pick my acidifier? Well, if you were to talk to a chemist, they would say the simplest thing to look at is the pKa, which is a measure of the strength of an acid based on its willingness to give up that hydrogen ion. The lower the pKa, kind of like pH, the stronger the acid, just like a lower pH is representative of a more acidic environment. The inorganic acids, like hydrochloric acid, are going to have pKa's below 0, which is why you have that complete dissociation. But the organic acids are going to have pHs anywhere between 3 to 7. And so what you can see here is that formic acid has a fairly low pKa, which is the basis for our AMASIL product. But this is on a molar basis. We don't add ingredients on a per molecule basis or how many thousands or millions of molecules we're adding. We add it based on the weight of it, where density comes into things. And so as you can see in this blue column here, formic acid has probably the best combination between low pKa to give you very strong acid, while still being an organic acid, but then also offering high molecular density, because this is the active ingredient. The more hydrogen ions you can deliver in a pound of feed means you're going to get more hydrogen, you're going to get more effectiveness from that acid. And formic acid is going to give you more bang for your buck as a result, because you're getting a lot more acid per space allotment in your diet. Taking a step to the side, we're going to talk a little bit about something called the minimum inhibitory concentration, often abbreviated as MIC. This is fairly straightforward. This is the minimum concentration at which a chemical will start to inhibit the growth of bacteria. So in this case here, we've got the blue bar representing where the minimum inhibitory concentration is for the chemical on this petri dish. And this is just an illustrative example to help understand what this is. And what minimum inhibitory concentration is usually used for is as a way to kind of rank products, to compare them against each other under same conditions to see which ones have the most potency under those conditions. And so we've got here are representations of two different trials that were conducted. The first is Strauss and Haller, which is the images on with the three different bars representing formic acid in green, propionic acid in blue, and lactic acid in orange. And as you can see, with a range of potential bacteria that you might want to control and feed, formic acid requires anywhere between half to a third as much product to start inhibiting the growth of these bacteria in feed on average. And in the graph on the other side, we've got only two bacteria, Staphylococcus aureus and E. coli, but we look at a range of acidifiers. And here's where you see these are all organic acids, but the density of these acids and the pKa's are different. And as you can see, formic acid under laboratory conditions requires about 1/8 to 1/10 of as much material to start inhibiting growth as, say, butyric acid, which is a big topic these days around gut development. So in summary, feed acidification is about more than just feed. Organic acids such as formic acid deliver unique value relative to the inorganic acids, and one must consider both pKa and molecular density when selecting a feed acidifier to make sure you give something that's going to deliver the value that you want in the amount of space you're willing to allow it in your feed. And in my admittedly biased opinion, formic acid offers the best in-class value as a feed acidifier. Thank you.